All right, statistics part 3. You're almost there. There's only one more after this, statistics part 4. This one tonight is largely conceptual in nature. And statistics part 4 will be taking the concept in this lecture and actually doing the math. And I'm going to point out in this lecture where those points of math are so you can focus on understanding the concept in those sections. For this lecture, we're going to use a particular data set for the whole thing, and we're going to walk through it and see exactly how we can analyze that data. And that data is going to be, how does the amount of sleep impact test score? Now here, we've got two different variables. We have our first variable, which is sleep. That's going to be our independent variable. And then we're going to have test scores, which is our dependent variable. And here I'm going to give you a data set, a sample data set that looks like this. So hours of sleep versus exam score. And we're going to go through and analyze this and see exactly how does the amount of sleep impact the test score. And we're going to figure out how much of the variation does sleep explain in test score. And that'll make more sense in just a little bit. To start with, we're going to have to look at what we call our descriptive statistics. And descriptive statistics are the things that I showed you how to calculate in the last video. That's your mean, your variance, and your standard deviation. So our mean, as we know this is the formula for mean, is going to be, on this case, it's going to be 75.3%. That's not a bad average exam score. It's not great. It's not terrible either. So now, once we have our deviations, our average, right? Then we're going to look up and we're going to look at our variation, which remember, all we're doing here is we're summing up all of the square deviations. And if we add up all of the variation, we're going to get 3,586.9% squared. Now, I want to emphasize again the units here that these are in percent squared, which is a relatively meaningless unit by itself. However, variation does on its own have a very important purpose, which we're going to get into in this lecture. But if you want to be able to graph something, we need to work down towards units that make sense. And so we first need to find out what the average variation is. So our variance is our average variation, as we discussed in the last lecture. And for this data set, that is going to be 275.9% squared. Then the last step, all we have to do is take the square root of this variance, and that's going to give us 16.6%. So that's our standard deviation. Now what we want to jump in and do is actually plot. Now that we have these descriptive statistics, we want to look at our normal distribution. Here is our normal distribution for the exam scores. Now what we're going to first do is we're going to get rid of this 0 here because our mean, our average, is not 0. And instead, we're going to make that our 75.3%. So this center line is going to be 75.3%. And then we're going to add in all of the numbers above and below it for +1 and -1 standard deviation. So we figure out what that is on the graph here. That's going to be 75.3 minus 1 times 16.6%. Remember, that was our standard deviation. So we got the -1, and that gives us a value of 58.6%. And if we go the other way, we're going to add 1 standard deviation. So 75.3 plus 1 times 16.6. And that gives us 91.9%. Now, if I were to draw the lines right here up like this area under the curve between plus and -1 standard deviation, the total probability that that would encompass, because remember this axis is probability, the percentage of probability that this would encompass would be approximately 68%. By definition, plus or minus 1 standard deviation means 68% of the probability. All right, but now we can keep going out further, and we could put in our 2 standard deviations. And the same process. So it's going to be 75.3 minus 2 times 16.6. And we're going to get 42.1%. And you go the other way, you're going to get 108.5%. Now, we've exceeded the exam score, and this is where you sometimes have to use a little bit of rational thought. Of course, no one's going to get an exam score of 108.5%, but this is a purely mathematical distribution curve. So you just have to remember that sometimes the values might exceed the actual reality of the situation. But in a pure math terms, this is what it would break out to be. Okay, and then at 3 standard deviations, you go all the way down to 25.5%, and then all the way up to 125.1%. So this is our normal distribution. What we're saying here is what this means is, remember, this is a probability distribution. So what that means is that we're assuming that test scores, we can't account for why a person gets a test score of one thing versus another. So the question we want to answer here is, how can we explain the variation in the data? Which is saying, why isn't every score 75.3%? Why does one person get a higher score and another person get a lower score? So we want to try to explain that, because right now all we have is a set of probabilities where any person might get any score. It's totally random, and we have no explanation for why a person gets a higher or lower score. So the question we're looking for is, what is causing some scores to be higher or lower than the mean? The mean is very important in this case. All right, and so in order to do that, we propose a hypothesis, which you saw in the beginning, which is that maybe we can explain some of this variation through the amount of sleep the student got the night before. And I'm going to show you how we're going to connect those two variables to try and explain that variation. The first quantity you have to understand is covariance. Now, we went over this in class briefly, but again, it's variance, which is the average variation, but it's co, meaning together. So you're looking at how the two variables vary together. And the way we're going to look at that is that if one variable's variation gets bigger, does the other variable's variation get bigger also, or does it get smaller? How are they changing together? All right, and the formula that we used for variance, now not covariance, the one we used for variance, was that you just took your deviations and squared them. And the units of variance was percent squared in this case. Now for covariance, we still need to have those same units of percent squared because it is a variance. So we're going to do that by taking the deviation of one variable, x, the independent variable, and multiplying by the deviation of the y variable. Now, remember, if you add up all of the deviations of one of these variables together, you would just get 0 by definition of what an average is. But in this case, we're not adding and then multiplying, we're multiplying and then adding. So we're multiplying each of these together down here. That's a terrible multiplication sign, but we're multiplying these together, and then we're going to add them. So as a result, the sum will not come to be 0, and our covariance does have a meaning that we can use. To understand covariance, we have to take a step back and look at variation. That is the sum of all square deviations. Let's look at two different ways in which you can kind of think about this. One is this circle diagram. Think of it like a Venn diagram that shows all of the variation that we had from our dependent variable. And we calculated that before. It was about 3,500% squared. So that's all the variation we want to try to explain with our model, and our model being that sleep explains the exam score. So now down here on the bottom, I also have drawn a normal curve. And that normal curve is representative of that same total, the total dependent variable variation. Now, remember that this is a probability curve. And so the probability curve always has the y-axis being probability. So what this says is that if I don't explain any of the variation, then it is left as a totally random variable, and whenever I take an exam score, the score could be any number and there's no way to predict it, which would make it a random variable. When we add in our model, that is our sleep, as an explanation for it, we decrease the amount of randomness that is left in the dependent variable, the things we haven't explained. All right, so if I decrease the variation, I decrease the spread of that normal curve, and it gets smaller. But then if I increase the variation, then I increase the spread. But regardless, the goal is to explain away that random part of it that I can't anticipate. And the way we're going to do that, again, is through the variation in the sleep. So what we're going to say is that the variation in the sleep can help explain the variation in the exam scores. And so we end up overlaying those two a little bit like a Venn diagram, and we call that area in between, that's shared between the exam score and the sleep, the dependent and independent variable, we call that the covariance. And so once we've accounted for that covariance piece, the stuff that's left, that's this thing that's still just pure blue on the outside there that doesn't have the overlap, we call that a smaller amount that's the sum of the squares of the residual, or rather the unexplained dependent variable variation. So we call that sum of squares residual, meaning what's left over. And if you notice here, I drew it as a smaller normal curve because it's smaller than the total. It's some percentage of the total that we haven't explained. So if you were to take the total variation explained by the covariance plus the residual, you would end up back with the total again. So you're just looking to explain as much as possible. And so as you pull that over, you explain more and more of that residual, and you want to shrink it down. That's the goal that we're looking to do. Now, what we're going to look at is how you can visualize this in a different way on an XY graph. On the scatter plot, what does this look like? So now, to visualize the same idea on an XY plot, we do just what I'm showing here. We plot our 14 data points that we have that was in the table before, and then we perform what's called a linear regression. And a linear regression gives you a regression line. And that regression line is your model. That's showing you how much of the variation is explained by the sleep hours or by the independent variable. And so ideally, if our independent variable explained 100% of the variation, meaning that the two circles were perfectly over top of each other, all of these data points would be right on the line. They'd be perfectly on the regression line, but they're not. They're slightly off. So I've explained sleep as a reason for variation, so why isn't everything on the line? Well, the reason that everything's not on the line is because sleep can't explain all the reasons as to why a person would get an exam score higher or lower. So what is left over, that sum of the squares residual, that part of the normal curve that you haven't explained is still present. So I'm going to draw this normal curve here, and what it is that at each point on here, each possible sleep value or exam value, there's still a certain unexplained variance, which is random. And so what we're going to do is we're going to turn this residual unexplained variation to the side, just like this. So that, let me get my highlighter out here. Right at this point here, we still have variation above and below based on some standard deviation that might be. As we move along, we'll get another one right here that it's going to have some standard deviation. Now, in most cases, we assume the standard deviation is the same all the way along. So we can do that at each point going up, all the way at every point, there's that same standard deviation curve of the unexplained residual that's still going to make it vary off of the line. But if we could explain 100% of the variation with a single independent variable, then this residual normal curve would collapse to nothing at all, and everything would be perfectly on the line. But it just doesn't work like that, especially in psychology when you've got many, many different factors. Sleep is probably not the highest factor that determines a person's exam score. You can think of other things that might do this. The number one would be how much has a person studied for the exam, or what is their mood? Have they had any life events? What did they eat for breakfast? These are all factors that come into play. So sleep is only one factor, so you're still going to have some residuals left over that are encompassed in those factors that we're not accounting for. Now, the next step in regression analysis is obviously to calculate out your parameters. When I say parameters, I mean the slope and the intercept of that regression line. So we need to have our basic formula down, which everybody should know already, y equals mx plus b. And what we're trying to calculate out is the m and the b, the slope and the intercept. We're going to have our dependent and independent variables, y and x, and then we're also going to have our two parameters, the slope parameter and the intercept parameter. Now, to calculate out the slope, all you have to do is take either your covariance divided by your variance, or you can do it this longer way, but from the worksheet that you have, this has those numbers in the bottom tabulated already. So now again here, what you're going to see is that you don't have covariance and variance, both are divided by n minus 1, but you don't see that n minus 1 here. And the reason you don't see that n minus 1 is because if I were to take divided by n minus 1 and divide by n minus 1 on both of these, they're just going to cancel out anyway. So they've already been canceled out in this formula. That's why you don't see them there. So both of these will give you the same answer either way. So the covariance divided by the variance of x, that's your independent variable, that's how you calculate out the slope. Now, if we do that for our example of sleep versus test scores, we're going to get 29.7 hour percent divided by 4.3 hours squared. And that's going to give us a slope of 6.9% per hour of sleep. So for every hour of sleep that you get, you should get 6.9% higher on the exam, is basically what that's saying. Now, that's the straightforward calculation. Calculating out the intercept is even easier. So all you have to do then is plug in the mean values for each one. So you note here that these now have the bar over top of them. So these are the sample mean values. So the y mean equals m x mean plus b, which we've already calculated out. So all you have to do is use those standard values. And if we rearrange the equation, we can solve for b by taking the mean of y minus m times the mean of x. And if we do those for our numbers, then we're going to have 75.3%, that's the average of y, minus 6.9% per hour times 4.8 hours, which is the average of x, and that's going to equal b. So that's going to give us an intercept on this regression line, our model, of b equals 42.2%. So that's the place where the regression line intercepts the y-axis. Okay, now on to our next bit. The question still remains as to how much of the variation does sleep explain our data set? That is, exactly how much. Now what I'd like you to do now is just by visual inspection take a guess. How much of the variation do you think is explained by sleep according to this data? Would you say it's 70%? Maybe 80%? Would it be as much as 90%? So what's the actual percentage of variation explained? So that would be everything that the covariance or the overlap of those circles is covering. How much would that be? Well, the exact answer is 73.7% of the variation is explained. Now, is that realistic? Not really. This is a fake data set. Would you really expect that however much someone slept, that you could explain their exam scores to a degree of 73.7%? No, probably not. Probably other factors that should be larger than sleep would be percentage of time or how much time you studied, what did you eat for breakfast, what was your mood, do you have any life events, what's your background with this subject. Those are all other factors that should be higher than this one. But nevertheless, we're going to work with this data set because it gives us this nice slope to work with here, and we're going to continue with that. The opposite of this would be something that doesn't have much of an impact. So how much of variation does ice cream explain in the data? So this is ounces of ice cream that the students had before they took their exam. So as you can see, the line is much more shallow and the data points are much more spread out from the regression line, meaning that less of the variation is explained. So what would you guess would be the percentage of variation explained in this example? Would it be 0% or 10%? Would it be as high as 20%? So look at the slope of the line and look at how spread out the data is from that line. What would you guess? Okay, so the exact answer is 3.0% of the variation is explained by ounces of ice cream. Now you have to think for a minute as to whether or not that 3% is real. It could just be that it's a statistical anomaly, meaning that our sample size was only 14 students. So could we generalize to say that in the population that it can be expected that 3% of the variation is explained by ice cream intake? Well, probably not. What this is probably more likely is that the 14 students just happened to come out with this correlation in kind of a random fashion, because 3% is so small that it might vary very easily to 0 on the population. So it's not really a very reliable number, especially given the small percentage that it explains and the small sample size. Now we're going to return to the math for a bit and look at a new measure called correlation. What correlation is a standardized measure of how related two variables are. Now this differs from covariance in that covariance has units attached to it that are always whatever the independent and dependent variable are. In this example we looked at two. We looked at ounces of ice cream and exam score. So those would be ounces %. And then we looked at another one which was sleep and test scores, which would be hours %. Now those are covariance units. And there's a problem with that in that if you want to compare two different data sets or two different measures, you can't compare the covariances because the units are different. So what correlation allows you to do is create a standardized measure that is unitless so that way you can do a comparison across different data sets and look at how correlated they are irrespective of their units. And so when we do that, we end up with a measure that goes from -1 to +1 or -100 to +100. And so here's the formula we use to actually calculate out the correlation. And it looks like this. So simply put, it is the covariance over top of the square root of the variance of x and the variance of y. So you calculated out all these already previously, and so we just divide out the two on here. Now what you're going to notice from the actual written out summation section is that we're missing that n-1 term here. But that's because here on the top part, covariance, it would be the sum of the deviation of x times the sum of the deviation of y, and that would be divided by n-1. Now over here, the variance would actually be over n-1 and then over n-1. And then remember, you got the square root here. So what ends up happening as a result is that all these n-1s cancel out. So this formula, even though it's missing the n-1 term, is the same thing. It'll give you the same answer as this one, the covariance divided by the square root, the variance of x, variance of y. And that's what the correlation is. It's a standard measure to be able to compare how related they are, because covariance does not allow you to do that. Now if we do that for our data set, that is the sleep versus exam score, we are going to have 29.7 hour %, that's the covariance, divided by what is the variance of x, 4.3 hours squared, times 275.9% squared. And that gives us an answer of a correlation that is 85.9%. Again, that's not very realistic and it's a fake data set. But if you crunch the numbers on this, that's what you'll get out of it. Okay, so now one more note on correlation. You can understand correlation just by visual inspection, and it's always a good idea to plot your data before you really do any analysis, and that can give you a good idea of what you're looking at and what you might expect from the numerical results, and it'll tell you if you did anything wrong. And so here you'll see I have shown a couple of different random data sets here that have different correlations. And you'll see it down here, we have a strong positive correlation, meaning that as the independent variable increases, the dependent variable increases also, with very little residual variation, not very much off the line. Now, a strong negative correlation would be very little residuals, but that it would be that as the independent variable increases, the dependent variable decreases. So it would be the opposite. And so that's what we're looking at in all of these. So weak positive would be high residuals, and as independent variable increases, dependent increases. Moderate negative, that was really terrible. So let's try that again, right through there. And then now if we had no correlation at all, what truly no correlation, what you'd end up with was a flat line that just went directly through the center with no up or down deviation. All right, and then a weak negative correlation like that. So you can always do them by visual inspection. Our last measure for the day that we're going to learn, our last new measure, is what's called the coefficient of determination. Now that's the official terminology for this quantity, but really nobody calls it that. Even professional statisticians just call it R squared. R squared is a number, is the percentage of variation that's explained. That's what this number is. So that when we were talking about the covariance, this shaded in area here, the amount of that, well, the percentage of the total variation that takes up is R squared. So that's what it tells us. So since that's a percentage, it can be any number from 0 to +1, 0 to 100%. And now the reason that it is called R squared, capital R squared, is because all it is the correlation squared. It's not very complicated. If you have your correlation number, it's just the correlation squared. Now here's where you're going to have to be careful though, is that the unit itself, the unit of this R squared is R squared. This number 2 in here is not actually a mathematical symbol. That is part of the unit symbol itself. It doesn't telling you to square. There is no such number, capital R. It's just telling you that it's the name of the unit is R squared. However, on this side, this is actually a mathematical symbol. You are squaring the correlation. So just remember that R squared, when you see that 2, it's all part of the same symbol. So don't let that confuse you. So R squared is the percentage of variation that is explained by the independent variable. That's what it is. And so if we use that for our data set, we're going to get our correlation number, which we had on the last slide, which was 85.9%. And if we square it, we're going to get what I told you it was before, 0.737, 73.7%. And so again, it is just telling you how much of my variation is explained by the independent variable. That's what R squared is. Here's our final slide from this lecture. And what this is meant to be is a summary conceptual slide that you're going to see all the visualizations that we've gone over from this lecture and the previous ones all summed up right here. And we want you to pay very close attention to this animation, and you have to understand how each one of these different pieces is interrelated and how as one changes, they all affect the other ones together. If you can understand all these different visualizations and their connection with each other, then you understand statistics perfectly. So just focus on understanding how this all works. And what you're going to see here is that the dependent variable variation circle is going to get more and more overlapped by the independent variable variation. And what that visualizes is more and more of that variation being explained away by the independent variable. And so the variation explained by the independent variable in the upper right-hand corner is going to increase from 0 to 100% as that circle overlaps it more and more, because that's all it is how much of those two circles are overlapping. Now, on the bottom left-hand side, you're going to have the unexplained dependent variable variation. That's the sum of squares residual. That's how much of your variation is not explained and therefore still a random variable and could have any probability in there and come out to be any value. So that is going to get more and more narrow as more of the variance is explained away. As that variation is explained, you're not going to have as much randomness in your data anymore, and you're just going to be left with explainable data. And finally, on the lower right-hand side, what you're going to have is you're going to see the XY plot with the regression line. Now, as that line starts to tilt up, that's going to be at the same time as more of the variation is explained because you're getting a higher correlation between the data. And then as that gets explained, you're going to end up seeing all of those data points come onto that same regression line so that there's no more residuals left. Remember, if that sum of the squares residual gets more and more narrow, as should the data points away from that regression line. They should get closer and closer to the regression line. So if the residuals come to be 0, then all of the data points should also be 0 deviation from the line. Okay, so here we go. Let's watch the animation, and you should go back and watch this a couple times. Okay, that's it. That's all of lecture 3. If you understand all those moving pieces, then you got it. All right, see you in the next lecture.
That's all, folks.